share the slides. Oh, Mac kurang sihat juga. Sorry. Okay, harap semua okay. We get better, right? Inshallah. Okay, let's move on. Yesterday we have learned about the 8 steps in lithography process. Sorry, just to confirm, you can see the screen, right? Just in case. Okay, cool. So we have discussed a little bit on the 8 steps in lithography process. So this is expanded from the basic that we call CED, right? Coating, exposure, and development. But before that and in between, you have other steps. For example, vapor priming in order to apply HMDS addition layer, just like a glue layer, so that the spin-coated resist can stick properly to the surface of the oxide. And then we'll have soft bake and cool plate in between, and then alignment, hard bake, PEB before that, hard bake, and then finally develop, inspect, or visual inspection. So today we're going to look at each of the 8 processes. So let's look at the first one, vapor priming. So we use HMDS as the addition layer. So the objective of this step is to apply a layer which the resist can adhere to. So for example, if you have completed your CED process, but say if you see your patterns, the printed resist are not staying upright, for example, ataupun dia sengat, ataupun dia collapse, maksudnya say you supposed to print something like this, features, tapi bila you do your visual inspection after the CED, you can see that the patterns are perhaps like that, sengat ataupun terbalik kan. So that's one of the signs that your HMDS may not be working properly. Okay, so that's one of the signs, but that may not be the exact root cause, but that could be one of the potential root causes, right? So what we do is we apply this HMDS in the form of vapor at certain temperature in order to promote addition of photoresist to the wafer. Okay, so we use hexamethyl disilazane, and then the process is run at typically 90 degrees or so for like 30 seconds. So this is how the chamber of HMDS looks like, and the vapor is applied from the outside to into the chamber. HMDS ni, have you ever done any work on HMDS before? Have you ever dealt with HMDS? Anyone? Dia punya bau dia, you can never imagine. The smell is like telur ayam yang buruk, telur ayam dah rosak. So that's the smells like. Okay, you talk about HMDS smell, the good one, the fresh HMDS punya smell. Macam tu dia punya bau. Kalau you buka punya bottle, so you have to install the bottle. Normally this is done by equipment technician. You install the HMDS bottle to top up every time, then you're gonna have tubing connecting the bottle to a chamber, and then the process will run. Tapi kalau you buka apa ni bottle tu while before you connect the tubing for connection, then you're gonna get some smell, and the smell is terrible. Okay, so that is HMDS for priming purpose, to make sure that we will have good addition of the resist to the wafer eventually, and the patterns to the wafer eventually. Right, the next step is spin coating, where we spin the resist. So normally, well, this depends on technology, on the layers. Last time, when I was in charge of the equipment, so the dispensing process of the resist uses about 1 ml. So 1 ml per dispense. So you're going to have a nozzle here. There's a nozzle. Wah, so the nozzle, then they can dispense the resist 1 ml, then will be followed by spin coating. So this is dispense here, and then it's going to be spin. Normally for recipe for coating process, normally you will have, I think, about 11 to 12 steps in a single recipe in order to do the coating alone. So the recipe takes about 11 or 12 steps in order to start the process, do the process, and finish the process. Okay, so just like what we can see here, spin off, and then solvent evaporation at the end. So the wafer is held by a vacuum chuck. So kita dah discuss, I think in the last lecture yesterday, we talked about a vacuum chuck where you have to turn on, the vacuum will be turned on when the robot arm places the wafer on the stage. Then the vacuum will be on, then only the dispensing will start, right? So if the vacuum has some failure, then if you spin at high RPM, you're gonna have wafer breakage. So just imagine the breakage at high RPM, like 3000, 4000 RPM. So you're gonna have the wafer shattered, pecah kecil-kecil ya. So at that point, if you have wafer breakage problem, so equipment memang kena down, process shutdown, equipment shutdown, then the technicians need to stop the machine, open the coating chamber, remove everything. Macam pinggan pecah kat atas lantai, you have to remove everything, clean the shattered plate, for example, then start vacuuming the whole places. Vacuum dalam chamber sampai super clean. Then you have to run, before you release the equipment back to mass production, you have to run test wafers. Okay? Run test wafers. This is how it goes in fab. So if you have any problem and the equipment is down and the process is down, before you release the equipment or the process to run mass production, like the original case, you always have to run some test wafers first. If any wafer kosong to run dummy process in order to make sure that the whole equipment, the whole process fits, and they have to do certain characterization to check and make sure that everything is fine. Then the moment that everything is confirmed to be fine, then only you release the equipment or the process to run mass production. Okay, so there's always an intermediate step running test wafers, or we also call it qualification process, qual. Kalau kat situ kami panggil qualification. So you need to run certain tests and measure and see if they're okay. And if the qual pass, then you release the equipment or the process to run mass production as usual. Okay, so the dispensing 5 ml here is very subjective. What we have in Soltera is about 1 ml. I'm not sure about now. Some, if you really need to run a thick photoresist thickness, then you may need to dispense high volume, like 3 ml, 5 ml. Okay, so the spin speed really depends on what sort of thickness are you looking at, and the resist viscosity. Okay, resist dia boleh jadi yang viscous one, viscous yang pekat punya, ataupun yang very diluted one, yang low viscosity. So normally if you run, if you dispense viscous photoresist, then you tend to have thicker photoresist thickness. Okay, sebab dia tebal. On the other hand, if you run less viscous photoresist, if you run the process at the same RPM, you will get a thinner photoresist thickness. So it really depends on what sort of thickness are you looking at and what sort of structures are you going to print in the CAD. So that will determine the process recipe for the coating, right? So there are a few parameters that you have to look at for the coating process. For example, the coating time, coating speed, RPM, the thickness intended, uniformity. You have to make sure that the whole thickness, katalah you spin di dapat resist thickness, you have to make sure that the thickness across the surface is very uniform. Okay, so to be able to check on the uniformity, so that means katalah ni wafer, this is the notch. So to make sure that you can deliver high uniformity thickness, you always have to run qual process, qualification, and measure few spots. So say in this case, katalah 5, but that's normally not enough. You'll probably run like that, or in fact more. Kalau you run more points, then you're going to have more data for your uniformity. Okay. So semua ni kita akan buat during qual. Qual ni kita akan buat either when the equipment is down or process is down, or after every PM. PM, what is PM? Any idea what is PM? Anyone knows what is PM as far as equipment is concerned? Apa maksud PM? So, PM is preventive maintenance. Okay, dalam if you run industry, if you run mass production, every equipment needs a PM. Preventive maintenance. Macam service lah, service. It's scheduled service. Preventive maintenance. So for example, if you talk about track, then that means cleaning up the coater cup, cleaning up the developer cup, cleaning up the robotic arm. Walaupun tak ada nampak kotor, tak ada issue, tapi you still have to do the PM. So it's preventive maintenance that is scheduled at certain frequencies. For example, if you talk about track, yang buat coating and development ni, so we used to have weekly PM every week, right? Weekly every week lah. Bi-weekly every 2 weeks, monthly PM every month, and then quarterly PM every quarter, semi-annual PM every 6 months, annual PM every 1 year, right? So going from weekly PM to annual PM, your checklist for you to check and for you to perform gets longer and longer. Okay. So kalau annual PM tu you akan down for a very long time, perhaps 1 or 2 days to check many things. Weekly PM is a very fast one, normally under 1 hour. Okay, and the rest is like in between. Okay. So at this point, so the qualification you will do after PM and after every issue that you have before you release the equipment to mass production. Particle and defects are another aspect that you have to check, right? Then after spin coating, we send the wafers for soft bake, right? The goal is to improve photoresist to wafer addition, promotes resist uniformity on the wafer by the baking process, improve line width control during the etching. This will come a little bit later. So when you talk about line width, for example, then what we are saying is this. This is your silicon, this is your oxide. Say you are printing your resist here. So this is your CD, line width. CD is line width, huh? The width of the line width. Okay. If you are measuring hole, for example, then you are measuring this as your CD. So CD depends, line width depends on whether you're measuring lines or holes. So if it's line, then this is the one. If it's hole, then this is the one. Okay, that's why you have to define when we talk about printing holes or pillars yesterday, right? So then in that case, the pillars would be your line width. Okay, if you print hole, then the whole dimension will be your line width, right? So you have to know that. So drive off most of the solvent in photoresist by soft baking as well. Typical temperature is 9100 degrees C for about 30 seconds on a hot plate. And then, as I said yesterday, it's always followed by a cool plate, right? A hot plate is always followed by a cool plate. So this is how a hot plate looks like. Normally dia akan ada multiple heaters on under the wafer. Bila letak wafer tu dia akan ada banyak heater, banyak heating point, so that the uniformity is guaranteed during the process. You cannot afford to have only a single heater at one point to cover the whole 8-inch. That doesn't make sense. You need to have at least a couple of points, center and on the edges as well, right? Then alignment exposure for E exposure. Okay, so last time we used to start with contact and proximity printing. Dulu-dulu lama-lama dulu. So we start with this. Ni evolution, if you like, from top to down. Contact and proximity printing, where the printing is really in contact with the wafer. Okay, so we call it proximity. So ada gap control, a very small one, and then we move to one-to-one projection printing. Then there are a few parameters related, and then we move to step and repeat projection printing, and now we are using scanner, step and scan projection printing. Okay, so this is the latest one. In the previous system, we call it stepper. Sekarang kita pakai scanner. Stepper ni old version of scanner lah. It's very slow and old version sikit lah. So let's compare. For example, if you have contact printing, then you have light source, see the one on the left, and then you have optical system, lenses, then you have your mask, you have your photoresist, and then look at the mask and the photoresist, right? It's very, very close there in the contact printing mode. Then when you move to proximity printing, there's a small gap in between mask and the resist on the wafer. And then we are now using this system where you have lenses to reduce the size to be printed from the mask to the wafer. Okay. So if you look at the contact printing, for example, it's one-to-one. So whatever you have on the mask will be printed with the exact dimension on the wafer. Okay. Capable of resolution down to about 0.1 micron, mainly in research mode. Proximity 1-to-1, 2.2 to 4 micron, low cost. And projection, you can reduce 4 or 5 to 1. So that means whatever you have on the mask will be reduced by 4 to 5 times on the wafer. Okay. So this itself has a couple of models, just like what we discussed yesterday about the ASML scanner. So up until what we have now, which is EUV, right? Which is down to a single digit nanometer. So this is how the system looks like, roughly. Tapi kalau nak tengok the exact system, I've uploaded a file yesterday about ASML in 1 minute. You can see how the system works in terms of the wafer stage, exposure stage, the interferometer, the alignment. You can see all the details there. Need just a very simple, simplistic representation of the system. Okay, but this is not everything. Dia nak bagi idea ya. So you start off with the UV light source on top, whether it's DUV or ARF or whatever. And then you have your laser. So if you talk about KRF, for example, then we are working with KRF 248 nanometer deep UV. Okay, so if you're talking about ARF, then we're looking at 193 nanometers. So the laser source will change. Then you have shutter to control the opening and the closing of the exposure, the whole system. And then you have reticle, which is the mask that carries the circuits to be printed. And we have projection lens to reduce the size, 4-to-1, 5-to-1. And then we have the stage. Okay, we can stay on the stage for exposure. And then for the stage control, you have X, Y, Z, theta. Okay. tengok the way it works exactly, just go on the YouTube video on ELEARN, right? You can see the complexity, and then the two stages running at the same time. One is handling the wafer that's just coming into the system, and the other one at the same time is moving as well and doing the exposure. It's very complicated, right? Right, resolution of features. How small can we print? So you can see here, moving from a big feature to a very small feature. So it's driven by this, it's governed by this equation, R equals to K lambda over NA, right? What is K? K is the process factor that represents specific application, typically in range of 0.6 to 0.8, okay? Lambda is the exposure wavelength of the system, so it depends whether you are using KRF or I-line, for example. You can come to this, for example, okay? For I-line, for deep UV. NA here is the numerical aperture of the lens used in the exposure system, in the scanner. Numerical aperture, NA, yeah? And these are the values, right? So calculating the resolution, so let me move this a little bit, right? Calculating resolution for a given lambda and A. Okay, for example, 0.6, if your NA is 0.45, for example, then you can calculate using the equation, okay? So this is the exposure system, just another representation of what we discussed on the previous page. And then you have your mask, dark field or clear field, and you have a lens in between for reduction. And then you have your wafer with resist on to be exposed. Okay, you can just plug in the values into this resolution equation to get the resolution. All right. Another aspect that's important in the scanner. This one is in the scanner, sebab scanner yang buat exposure. So it's not in the track, it's in the scanner. So see here, you have already got your photoresist. That means you have the wafer has gone through coating, and then soft bake, and then alignment, and then it's coming to exposure in the scanner, right? So resist. So this thickness is dependent on the depth of focus. Maksudnya kita tak set kita punya thickness tu suka-suka. So it's related to the optics of the exposure. Okay, so that's how these two parameters T and DOF are correlated. Are related, okay? Kita bukan suka-suka design the thickness, right? It depends on the DOF of the process. Okay, so you can see the center of focus here is somewhere in the middle of the resist, and then you have the depth, right? How deep, how big is the process window of that particular resist? So maksudnya dalam region DOF ni, you're gonna have good exposure for sure. Outside the DOF, bawah dengan atas, kalau you punya resist thickness terlebih thick, for example, then you punya focus outside the original region, say this is the original region, X will be poor. Okay, the resolution will be poor because the focus is poor. So remember, to generate the image, to print the image by light, you need to know the optimum DOF. Okay, maknanya you kena tahu kat mana dia optimum daripada depth of focus. Kalau you are out of focus, then you akan dapat feature yang tak sharp lah, out of focus. Just like when you want to capture a picture on your phone camera, for example, right? Certain images yang you nak ambil gambar jauh, then most of the time you have to print in the set, you have to press in the center of the screen to make sure that it's focused. If it's not autofocus, okay. Kalau nak ambil dekat, then the system, if it's on autofocus, then your optics will help to focus for the nearer image, right? So the same goes to this process. Maknanya dia akan optimize dia punya focus based on what we have in the process, right? So to calculate DOF, the equation is already given, lambda over 2NA squared, and NA is given by numerical aperture of the lens for the exposure. Okay, so you can see the illustration here. You have lens on top of the resist, and then the resist has a specific thickness, and then you can see the focus here. Macam belajar optik lo. 2 second year kan, belajar optik kan, 215 kan, if I'm not mistaken. You can see here the intersection point is in the middle of the resist, right in the middle of the resist. So if, for example, you have features printed after lithography which look very poor in resolution, tak sharp, ataupun they're distorted, so one of the reasons could be due to the focus. Depth of focus ataupun thickness of the resist is not correct, ataupun you punya exposure system has problem, or particles perhaps that could alter the DOF, right, and all the stuff. So you want to have a very smooth surface and the thickness is well in control, okay, in order to make sure that your DOF is fixed all the time. And this I can share on Elin some document on DOF. Right, this is another example, a very simplistic example of the exposure system. But this is nowhere near if you compare to EUV. Okay? Kita discuss malam EUV, you can see the cablings and all the stuff. The chambers, the tubing, the hardware, the modules. Saya ada capture semalam dalam group kan. More than what? How many parts? Yang saya letak dalam group tu. Let me have a look at it again. EUV, ya. Okay, each EUV machine has over 100,000 parts and cost 150 million. They are shipped in 40 freight containers or 4 jumbo jets. Okay, that's how complex the system is. So this is nowhere near. In fact, bila you nak buat installation, new equipment, sebelum ni, when you bring scanner, for example, shipping, bila sampai dekat airport, then truck atau container lah, container yang bawa scanner tu daripada airport, dari airport ke fab, dia kena travel at certain maximum speed only. Container tu dia tak boleh laju, I think 20 km per hour or so, if I'm not mistaken. Very slow lah, very slow. It cannot exceed the speed because nak jaga dia punya optics dalam sistem, and it cannot afford bad vibration. Kalau sikit-sikit okay. And if I'm not mistaken, dia tak boleh stop dekat traffic light juga, so dia kena ada escort dan traffic light kalau merah dia kena jalan je, sebab nak maintain the quality of the system that's being shipped in the container. Lari sikit optik, then the whole thing is gone. And banyak cerita lah, bila installation and commissioning is going to be very, very difficult to get the specs. Okay. Right, scanner projection aligner, this old system, very simple one. Again, back in the 90s, stepper system. Again, you can see on the video later on, it will give you a better picture of the current system. This is early 2000s, step and scan. You can see below the step and scan, you can see the way it scans, right? Below you ada kata ni reticle, so this is your reticle to be scanned. Okay, so the way it scan is there are certain patterns, so in this case it's going to follow like that. Okay, so dalam ni mungkin ada few fields that you want to expose, mungkin satu field ni satu die lah, so dia akan follow zigzaggy in this case, right? So they had every field, so every box here is called field of exposure. So then it's going to repeat. Dalam ni dia akan repeat patterns. So mungkin ada certain field yang berbeza dengan pattern, mungkin ada due to certain purposes, for example, for alignment's sake or for checking certain characteristics or for certain tests. Okay, so But in general, that's how it scans. Okay, so they can scan. So the way it scans, and how fast it scans, how many fields do you have, and the dose, kita panggil dose, exposure energy kita panggil dose. Energy we expose daripada illumination system, exposure energy lah, we call it as dose. Normally we use millijoule per cm squared. So every layer, every pattern that you want to print has its own associated dose. Okay, maknanya dia ada dose and focus lah, dose and focus. So we're gonna see later on. So these are among the main factors that you need to incorporate during the scanning process. Dan semua ni dose, focus, the way you scan, how many fields you have, how fast do you scan, in what patterns do you scan. So they are all together compiled in a file that we call job file. Job file. Ni very operational. Saya explain ni bukan fizik sangat. This is how it works in the fab, job file. So macam recipe lah, but we call job file on scanner. So kalau dia nak print layer A, for example, with certain thickness of photoresist from the track just now, and then you want to expose, so dia akan extract its related job file. Say job file X11 ke apa, ada nama lah based on the technology that you want to print. But all these parameters are compiled, are consolidated in a job file. So dalam tu ada dose, focus, field size, how many field, the way you scan, how fast you scan. Okay, when you load the job file, it's gonna do the job automatically sampai exposure completed, right? Job file. Okay, this one is the evolution of the light sources. Back in the 90s, from 436, the G line, H line, and then goes to I line, then goes to DUV 248, and then ARF 183, and then now it's EUV. Okay? EUV sekarang only 13.5 nanometer. So just look at the evolution from 400 plus down to 13.5 nanometer EUV. Okay, zaman dulu maksudnya tak ada lagi all the high-end chip semua tu. 5G lah, semua kan. Sekarang you have many things. Okay. AI, semua dulu tak ada lagi. So semua AI, 5G is enabled by EUV system. Okay. That's why EUV is very crucial in fabrication. Right, reticle is generally called mask, but mask ni normally kita associate to one-to-one pattern transfer. Means whatever you have on the mask is exactly transferred with the same size, one-to-one. Tapi reticle pun kita bagi mask juga, sebab dalam fab we know already that there's got to be reduction in the dimension of the circuit, and we call it mask anyway. Tapi kalau you look at the terminology, mask ni usually we call it as one-to-one transfer. But the moment you have reduction, we call it reticle. Okay, we call reticle. So kalau tengok kat sini, reduction for mask, difficult to pattern submicron dimension on mask and wafer without reduction optics. So there's no reduction optics. So that's why your pattern is transferred one-to-one. Kalau you ada 500 nanometer of features of CD on the mask, so you're gonna get 500 nanometers exactly on the resist as well. Okay. Tapi kalau you ada 500 nanometer on the reticle, so if you assume 4 times reduction, so that will be 125 on the resist. Okay, due to the reduction optics, projection optics. Okay, few parameters to look at: CD, critical dimension, depending on your printing, the lines or the holes. Okay, and if you talk about fab, CD, kalau cakap tentang CD ni, you even have 2 types of CD in the fab. Okay, kita akan belajar later on, but let me just introduce you. When you print your features, okay, macam tu, kalau dari print line, and this is your CD. If you measure your CD after litho step, after CD, we call it as DICD. Ini operational. Maksudnya operational, I mean yang fab dia panggil apa lah, macam tu lah. So that you know, okay, bila sebut DICD, oh okay, belajar lah. CD ni is a very general, tapi DICD here means the CD that is measured after CED process, and that's called develop, inspect, CD. Develop, inspect, CD, ataupun DICD. Okay, so the next process after lithography, we're going to learn about etching. Okay, so after etching, dia akan ada CD juga. So we're going to learn later on. Draw kat bawah ni. It's also called CD, but then it's not called CD in general. It's called FICD. Final Inspection CD. Ini CD yang last lah. Final Inspection CD. Jadi Develop Inspection CD. Okay. So final means you cannot change already. Okay. Kalau DICD, in the real fab application, if you have a problem with your DICD, so remember last time we talked about SPC chart, the fluctuation of your data of your CD in your process spec, within your process spec. Kalau ada problem in litho process, you can still redo the process. Maksudnya redo the process ni kita panggil rework. Okay. Rework means after you've done your CED, then you do the measurement, CD, inspection, overlay. Tiba-tiba one of the specs tak met atau out of spec ataupun dia fluctuating on the higher side of the limit or the lower side ataupun they're almost out. Okay, you can actually rework the whole litho process. Rework here means you strip off the resist and start all over again. Okay, you strip off the resist. Ada dalam proses yang kita akan belajar later on, etch. Dia akan, you hantar wafer pergi ke etching, dia akan remove all the resist, then you're going to be left with oxide on silicon as before CED. Okay, then wafer tu akan masuk balik kat photolithography process, then you're going to proceed your CED second time. Okay, so that is after rework. So this is the privilege of lithography process because you can do rework. So that's why the CD is not the final version. You can still rework if you have to. But the rework is controlled. The rework rate is controlled by operation. Kalau you buat rework, that means something is very wrong then. Okay? You want to minimize the rework, but then if there is any problem in the CED that you have measured and characterized, you can still rework if you have to, before it's etched. Tapi the moment you dah hantar pergi etch, you dah remove dah, then there's no more rework. Kalau ada problem after etch, you measure the FICD, ada fluctuation dan keluar daripada spec, you have to scrap the wafers. Scrap, habis, wafer is gone. Tak boleh pakai dah. Buang wafer tu. Okay. Kalau rework, maknanya you remove layer je, patah balik, boleh redo the CAD process. That's why we call it as DICD, develop, inspect. It's not yet final, but the moment you etch already, gone. Wafer is gone. Kalau you etch dah dekat, let's say your process cycle is like 3 months, and then this process is affected at 2 months, maknanya your whole 2 months is already gone if your wafer is scrap. 2 bulan tu gone, habis. All the expenses related to the particular wafers, habis, masuk longkang je. So that's why it's important to understand DICD, FICD. Okay, exposure field, mask technology, throughput. Throughput is how many wafers you can run through a system. Track ke, scanner ke, combination ke, right? Alignment and focus, you want to get the right alignment and focus. Defect has to be taken care of as well, depending on the limit. Surface flatness, so that you don't have any focus problem. Okay, so just imagine if you have some particles left on your oxide, you had a wafer, and then you had a particle here and there on your oxide, and then you miss, you tak contain wafer tu, dia pergi ke litho, dia akan go through coating, tapi bila you coat, apa yang dia kat atas wafer? Dia akan jadi bumpy, right? So apa jadi? Bila kena tanggung ke loss tu. Of course, you don't have to, but you tak larat dengar nanti ya. Satu wafer you scrap, say a wafer cost 1,000 USD, and then you scrap the whole pot 25,000 USD, and that's like 100,000 RM. So boleh beli kereta sebiji ya, kereta yang high end sebiji contoh ya. Then your boss probably says to you, your salary cannot even pay the loss. Then dia akan sebutlah kat Iblis Link, tak dengar. Okay, You don't have to pay, but then you will see this later on. Kalau you get to do internship atau you work in a fab, you will hear this eventually. Okay. Right. So okay, kalau you punya resist is bumpy, what do you expect to happen during the exposure? You have the particles during the oxide, but it's not captured. So the wafers proceed as normal. Then you spin coat the resist, and then you end up with bumpy resist coverage on the wafer, and then you go to exposure system. What do you expect to happen? Anyone? Ready? Exposure. Let's talk about exposure. Based on what we learned today. Let's have some guesses. What do you expect to have? Hadi? Hadi, what do you expect to have? If you have particles on the oxide covered by resist, so bila ada particle, then resist will be a bit bumpy. Then you send the wafers for exposure. What would you get? Apa jadi? Hadi? Before we finish the class today. Siapa nak bertukang kat atas ni? Saya kat office ni. Ada bertukang kat atas. Ada orang ni kot. Apa? Buat kapet kot. Sebab Faris. Faris, any guess what's going to happen? On, you can unmute yourself. Give some guesses. Not sure. Okay, others. Akilah. Akilah. Kakak apa dia, Akilah? It's okay. Just guess. See what happens. Ifah. Ifah, any guess? Apa jadi, Ifah? You want to have a very smooth surface, but then some particles are missed. And that's caused the particles to be under your resist. And then no one realized, and then the wafers go for exposure. What's going to happen during exposure? Anyone? Any guess at all? Kali, any guess, Kali? Teka je, it's okay. No worries. Logic, just common sense. There's no high-end ataupun state-of-the-art here, physics. Anything? Apa jadi kalau surface tu tak smooth, then you go for exposure. What would be, yep, go ahead.
Saya nak teka apa tu, resist tu dia takkan betul-betul affected dengan dia punya dengan UV lah, sebab dia punya jarak dah lain.
That's the key. That's the keyword. Jarak lain kan. If you go back to this, parameter, kita discuss apa parameternya? What is the main here? See, DOF. So just imagine kalau you ada particle bawah resist ni, apa jadi kat resist tu? Bumpy, right? So bumpy, what happens to the DOF? Scanner pening nanti dia nak fokus. Tengok, dia fokus kat sini, tinggi, fokus kat ni rendah. So dia tak tahu nak adjust fokus, tak tahu nak fix fokus. Sebab dia kena buat standard alignment and standard focus sebelum dia expose the energy, the exposure dose to the fields. Okay? So dia pening. Bila sampai kat field lain, dia mungkin akan recheck and then dia pening. Tinggi pula, rendah pula. So you end up having unoptimized focus everywhere. Okay? Bila you ada unoptimized focus, go back to the mechanism. Bila you expose positive resist, what's going to happen? Positive resist, exposed. Ready? Go back to the earlier mechanism in lithography.
Soluble.
Positive resist, soluble, right? Soluble. Okay? Area soluble pun dia akan jadi, here and there. Okay, ada perhaps partial removal of resist and all the stuff. And then you may end up with patterns that are not straight ataupun dia akan sengit sikit ke, ataupun dia tak intact lah. Okay, you tengok cross section, you measure sini 100 nanometer, you measure sini 110, 120 as a result of different focus. Okay, so it's going to affect your DOF, depth of focus. Okay, so that's the key. So soalan yang saya bagi ni soalan yang lebih applied in nature, application, real case. But it goes back to the DOF, to the mechanism, to the fundamental. Tapi soalan saya bagi tu ialah soalan-soalan what happens next using all the knowledge that you already have, right? So another, let's finish in like 5 minutes. Another parameter that you have to look at, bila you expose, as I said, I think yesterday, if you are exposing, katalah you punya whole process flow has 40 mask altogether from day 1 until the completion in 2 months. For example, you kena pakai 40 mask, 40 kali litho, sampailah complete device. Okay, then you are now running your 30th mask. You dah ada 29 layer sebelum ni yang dah litho. So this is the 30th litho in the device. Okay, so you need to align your current litho process to the previous litho process, your underlying layers. So that's why we need to measure another parameter that we call alignment, or we call it overlay. Oh, sorry. Overlay. Overlay ni kita nak measure how good is the alignment of the current layer to the previous layer. Okay, in terms of the Y alignment, Y shift, in terms of the X shift, in negative Y, negative X, just the other side. Okay, so you think, kalau you say you print this layer, the gray one, perfectly on the underlying layer, then you're going to have a perfect overlay accuracy. So that means your box, for example, if you want to print a box, as an example, is perfectly aligned in the box area. Okay, mana tak lari sikit pun, right? So it's called perfect overlay accuracy. On the other hand, on the right, if you have a shift in the overlay, so dia akan ada, you can see that you actually printed here a bit shifted from the intended box. So maksudnya you ada plus X here and negative Y here. Dia shift ke kanan dan bawah sikit kan. So dia akan lari. So that's why bila kita complete CAD, so on top of the CD measurement, visual inspection, overlay is another characterization that you have to do in order to make sure that your current layer is perfectly aligned to the previous layer. And this X and Y, and plus X, negative X, negative Y, and in fact theta pun ada, theta pun ada alignment, characterization. Semuanya ada dia punya own spec. So kata you punya spec SPC chart, statistical process control for X. So you're gonna have like target punya point and plus minus, and the same goes to Y, the same goes to theta. So you can SPC chart semua untuk control to tell whether you are printing the current layer perfectly on the previous layer. So so the bigger the features, katalah you talking about teknologi yang lama dulu, in the region of 400 nanometer punya technology node, then you punya margin for X, margin for Y will be bigger. If you talk about the current technology, for example, 14 nano, 7 nano, 5 nanometer, just imagine the overlay accuracy, the plus minus that you have to fit in order to deliver high performance chips, right? So overlay is another factor to look at. So this is the alignment. Tengok tadi macam kita belajar pasal scan tadi. So if you scan ni every field that you want to scan, then semua ni dia akan ada overlay dia. So this is another example. So to make sure that you have a perfect overlay or almost perfect overlay, bila you start your exposure system, there will be a global alignment. Bila you nak scan, before you print the pattern, there will be alignment punya mark. It's called alignment mark lah, alignment mark, reticle alignment mark, level alignment mark. So this has to be done first. Maksudnya scanner dia akan check the current alignment mark that is present on the current layer that is not that has to be aligned with. Okay, dia akan check alignment mark, tengok alignment mark okay, baru dia akan start printing. Kalau alignment mark tak jumpa, then it won't print because it will say dia akan bagi alarm fail global alignment, GA fail, GA error. So dia akan buat necessary step before it starts the printing process. Okay, so dia akan cari alignment mark. So it's very, very important. So on, how many more pages do I have? I think I'll just continue on Friday then. Okay, I'll continue PEB on Friday and then we'll move on to litho part 2. Okay. Okay, is it okay so far? Any questions do you have at this point? Oops. Any questions so far? Can everyone follow? Is it difficult already at this point? Fabrication? Tak usah. So semua boleh follow Masih okay, right? Okay, it's good. Sekarang week apa? Week 6 is it? I'm going to tell you about your test, okay? Little is great, okay, right? So I'm going to tell you about your test. I think the mid-sem break will be in week 9, kan? I think the test will be in week 8. And it's going to be open book test, as usual, S386. Okay, nanti I'm going to tell you the details perhaps this Friday to remind me of the test. Okay, so in 2 weeks' time. It's kind of week 6, so week 8, I think, before mid-sem break. So it's going to cover from day 1 until lithography. Okay, day 1 until lithography for test 1. Nanti saya akan bagi more details. Just a heads up to everyone, right? Okay, then I'll see you Friday, inshallah. Bye-bye. Take care. Assalamualaikum.